So today we're going to be taking a look at a macroscopic momentum balance or a force balance on a benchtop wind tunnel experiment. So in Senior Lab we have a benchtop experiment, and this experiment kind of looks like this. We have a rectangular duct . All right, and in this duct, we mount different objects. So in this case, I was solving this for a cylinder that was mounted in this duct. So something like this. And in this duct, we have a uniform flow of air that comes in. One end, and then what we do is we come in with a little measurement tool. This thing is called a pitot tube. And so the pitot tube is down here, it's open at one end. And this pitot tube, we scan back and forth. The pitot tube is for pressure measurement. It's hooked up to a manometer, which we learned about in Transport 1. But we take this and we scan it up and down across this rectangular prism, and we measure the velocity downstream of this object. And so that velocity profile might look like, say, a high velocity that actually reduces in the wake of this object. That might return to a higher velocity. And so the vectors that we draw might look something like this. And that's what we're trying to do. We're trying to measure this velocity profile and correlate it to the drag force that we could experience on this cylinder. All right, so that's what I want to do. And I'm going to use a macroscopic momentum balance to do this. So the equation that we had for a macroscopic balance was something like a change in the mass flow rate times the average velocity. So we're capturing kinetic energy in this term. This is going to be proportional to rho v squared if we take m dot and look at that as a rho va. This is going to be, we can have pressure acting on each face. We had a gravity term. I am not going to include the gravity term. Here we have airflow. Actually, in a very true sense, this wind tunnel is set up like this, so it's a top-down flow. But again, we don't expect much, if any, contribution from gravity here. If anything, we'd expect forces in gravity to be acting up and down the way we've drawn it here. Again, we're just going to neglect that because it's air. So we'll solve for some reaction force. My plan is to say that there's some reaction force that's required to hold this cylinder stationary in the presence of this fluid that has to then kind of move around this cylinder. And as I'm kind of describing the assumptions here, another assumption I'm making is that the viscous losses are practically negligible. So I've actually not drawn a no-slip boundary condition here, and I'm also going to neglect the shear on the cylinder as the fluid moves around it. So basically we're looking at the momentum displacement, right? How does this object displace the momentum, and then what's the force necessary to hold that still? So this equation could be equal to a change in momentum, right? We could say there's some change in momentum with time. But if we apply this drag force, if this reaction force is holding this cylinder stationary, where the air flowing, there is no change with time. And so this is the system, the equation we need to solve for this. So if I was actually looking at this in 3D, I would have solved for what we would say F sub d, the drag force. But I think it's perfectly fine to look at this in 2D, right? In fact, we scan across here in the very center. We don't ever scan, say, in and out of the page. So the system that I'm really analyzing is like this. It's a black box system, right? It's a macroscopic system. And then in this side, I have U infinity. And we'll have some pressure. So take green. So we have P naught upstream, and then downstream we have some exit pressure. In fact, it outlets to atmospheric pressure. Because it is a duct and we do have some object here, we do have a pressure buildup. So PO and PE are not necessarily the same. All right, and then out of this black box, we have something. In fact, I'm going to be a little careful about how I draw these vectors. This should be kind of smoothly connected. All right, and so I've purposefully drawn. Oops, you know, I didn't get quite. I need it to come back like this. All right, so the idea here, what I'm trying to capture is that if we follow any one streamline through here, this one might have to be something like this. But the exit velocity is not the same as U infinity. And in fact, if we even trace a streamline far away from this object, due to mass conservation, we know that if we're blocking off a significant portion of this flow, if we do a mass balance, say right here, and look at this as the inlet, and then each of these is an outlet, well, we had better have a higher velocity here because we have less of a flow area. And so here, if we have more flow because we have an obstruction, we're going to have a higher exit velocity. Here we'll have a lesser exit velocity. And so this is the system. I don't even care necessarily what the shape is. And in a two-dimensional sense, what I'm going to be solving for is what we call this D, just a capital D, and that's the drag force per unit length, two-dimensional drag force. So that's the system, this is the equation, and we'll draw this a little better because we've got some weird stuff going on here.